a press conference per se. It's what we call a backgrounder to get you prepared and get your minds set on this great new mission that's coming up next year. So assisting me today by monitoring our webcast is Deputy Press Officer Larry Marshall in the back. And I want to give a special shout out to Frank Reddy from NASA Goddard, who organized this seminar for science writers and got the team together to be with us today. So the way these briefings work, even though it isn't specifically a press conference, is I'll introduce everybody and then I'll turn it over to the first speaker. They'll speak in turn, and then when they're done, we'll do Q&A. All right. Please remember to silence your cell phones, so we don't want them going off during the briefing. So this is the first AAS meeting in quite some time when we haven't had a press conference dedicated to results from the Kepler Space Telescope. You all remember Kepler, still operating as K2. This is the NASA mission that really revolutionized exoplanet science. And now we're getting ready for the next revolution with the transiting exoplanet survey satellite, TESS. So we have the mission's principal investigator with us today, George Ricker from the Massachusetts Institute of Technology, and he and several of his team members are going to introduce us to this mission and what we can expect, what we should be looking for, and what kind of science we're going to see. And I'm sure it will dazzle us much the way Kepler did. So speaking after Dr. Ricker will be Sara Seager, also from MIT. She'll be talking about TESS's anticipated exoplanet bounty and some ground-based follow-up. Next will be Padi Boyd from the NASA Goddard Space Flight Center, talking about guest investigator program science. And finally, Elisa Quintana from the NASA Goddard Space Flight Center will talk about combining TESS with current, as in Hubble, and future, as in James Webb Space Telescope, missions. So with that, I will turn it over to George.
Thank you, Rick. Well, good afternoon, and it's a real pleasure to be here and to share with you some of the excitement that we think is going to be building over the next few months for TESS, and then some of the results that we are hoping for that would come from the mission. So what I'd like to begin by saying is that I'm representing a very large group of people who've dedicated close to 10 years of their lives in many cases, and devoted millions of person hours to actually preparing the hardware. We're getting very close to launch, as many of you heard. We're expecting that we're going to leave the integration site, which is currently out at Dulles, near Dulles Airport at Orbital ATK, and take the satellite to the launch site in about a month now. So the role that TESS actually has is shown in this slide, which is sort of the arc of missions that NASA has been presenting. There are other organizations besides NASA that are involved, but these are the ones that TESS is really designed to actually fulfill. TESS is going to launch in March according to the current plan, and it's really intended to bridge the capabilities that were provided by Kepler and the thousands of exoplanets that it discovered to actually providing information that will be useful for Webb and telescope missions that are yet to come. In fact, this is one of the major questions that TESS is intended to answer of where will we be pointing Webb. And so if you actually look at the role that TESS has in this and actually the respective size, this is what TESS looks like. It'll act as the finder scope. So TESS is tiny, but in some sense it punches well above its weight class in terms of what it can actually do to provide targets and open up the future for other missions that are yet to come. I'll just show a quick animation that describes what is a transit. Many of you may have seen this previously, but this is what happens when we have a condition where, in this case, a hot transiting Jupiter passes in front of its host star. You get a dip in the light, and that light dip in the case of an Earth-sized planet around a star like the Sun is actually quite small. It's about the order of 100 parts per million. This is what the cameras on TESS look like currently out at Dulles at Orbital ATK's facility. There actually are 4 cameras that were actually being optically tested here. One of them had the protective cover removed, and there was a light test that was actually being carried out. The green that you see in this is actually a reflection from an interference filter that's actually inserted within the camera elements itself. And the light that's actually passed by TESS to its detectors is actually redward of 600 nanometers. So most of the light that TESS will actually respond to is actually in the near infrared, not in the visible light. So this is what the integrated observatory looks like when it was actually being prepared a few weeks ago for the work that was done in the thermal vacuum facility at Orbital. The 2 technicians that you see give you a little bit of a scale size. This view actually makes TESS look a little bit bigger than it actually is. It's only about as high as I am, 1.5 meters, and it also has a total mass that's only about 300 kilograms. So in this view, you can actually see the actual images that are associated with the. This laser doesn't seem to work, but in any case, you can see the 4 objects that are inside the cone at the top, and those are in fact the cameras that are associated with TESS. There's a large dish that's covered with metallized material that you can see near the center of the image, and that's the telemetry dish that we actually use for bringing the TESS data to Earth. So TESS is actually going to fly in a rather unusual orbit. It's an orbit that provides an uninterrupted view for more than 90% of the sky. And the orbit is what's called a P/2 orbit with respect to the Moon. So the orbital period is actually about 1/2 that of the Moon, and it actually flies in resonance with the Moon. So this little animation shows how that works. Basically, we launch TESS in such a way that the Moon, and if you look where it is right now, when TESS is out at apogee, there's a right angle between TESS, the Earth, and the Moon. And so this relationship is one that actually helps to stabilize the orbit, because if I let the animation run a little bit further, when you reach the condition where the Moon is at the top of the view, then it's 90 degrees again. So basically what happens is the Moon is actually tugging on TESS in one direction half the time, and the other direction the other half of the orbit. And so the net result is that it actually stabilizes the orbit in a way that we don't have to use fuel or any other station keeping activities at all. It just stays in this orbit for many decades. And the reason that this is a major advantage by being in this particular orbit rather than some of the other orbits that people have considered for missions like this are given in these 7 points here. And the one that's most critical for a lot of the science return from TESS is the high data rate that's associated with it. And with those high data rates, you actually are able to bring back full-frame images from the mission. And that's one of the unique things that TESS brings that was not possible with Kepler. And so as a result, this is part of what TESS does that really builds on Kepler. It has the ability, and the way to see this is there's a phrase that astronomers use, étendue, which is a measure of the product of the solid angle being viewed and the number of photons that you're actually registering, and that product is about 5 times greater for TESS than it was for Kepler. So this is another animation that I'd like to share with you for a minute. This actually shows the way that Kepler actually views the sky, that TESS views the sky, and the 4 cameras are actually staggered in their orientation, so we look from the ecliptic up to the ecliptic pole. There's actually a small band of the ecliptic that TESS does not view in the primary mission. So as a result, the 4 cameras are abutted and look at a stripe of the sky that's about 2,000 square degrees altogether. And it stares at a given piece of the sky for one TESS orbit, the 27 days in 2 segments, and then it actually steps around roughly once every lunar month. And in so doing, we cover the southern hemisphere in the first year of the mission with 27 days of exposure on all parts of the sky. But more to the point, we also spend a lot of time looking at the ecliptic pole in the south, and then in the second year we repeat the survey for the northern hemisphere, and as a result we end up with a large, almost a year-long exposure in the south and north ecliptic poles, and those are the regions that are primary targets for Webb, because Webb can look at those particular parts of the sky at any given time. And in fact, for future missions that are going to be operating from the Earth-Sun L2 point, that's also going to be the case. So those are special areas of the sky that we put a lot of focus on. Now, the other thing that TESS has is the large fields of view, and this figure actually shows what the field of view from one TESS camera is. So it's 24 degrees on a side, and the 4 blocks that you see in this little checkerboard pattern are the 4 CCDs, and for scale you can see there's 1 square degree. So this is what the Kepler field of view looks like. So if you scale from this, you can see that indeed we're looking at about 20 times as large a solid angle at any given time. Now, in addition, the TESS is providing full-frame images from all of the objects in the field. In the case of Kepler, that was limited to a little bit under 200,000. So TESS is able to look at 30 million stars and galaxies at any given time, and we get these so-called full-frame images for each sky segment lasting for 27 days. So it's a very extensive survey. And just to give you an idea of the scale of TESS, that's what this figure shows. That's a constellation of Orion, which many people will recognize. So the takeaway from TESS that I'd like to leave you with is that the real focus is going to be on bright nearby host stars that will enable follow-up not only by Webb, but also by the upcoming giant 20, 30, and 40-meter telescopes. The operational life of the mission could very well extend for more than 2 decades. It's not limited by any of the resources that typically limit missions. And the targets are really going to be those that are bright and nearby in terms of their location in the solar neighborhood. That's what Sara will be talking about in a little bit in her presentation. And so therefore these targets are always going to have a special role for radial velocity mass measurements and other types of characterization that will be necessary to prove that if you find candidates in the habitable zone, are they potentially interesting from a biological point of view. And the full-frame images, in addition, are something that will be available to many other areas in astronomy and astrophysics for future study. Thank you.
I'm not sure if we're taking questions now, but I'm going to have to look for my talk.
Yeah,
I got it.
Yeah.
Yeah, but it's not what I saw before, but hopefully it's the same one. You might want to just change it for each person because it's sufficiently complicated. Hi, everybody. I'm Sara Seager from MIT. And just as George started out, I want to say that my talk represents literally millions of hours of work by a variety of different people. Before we can get to TESS Science, I wanted to share with you a little bit about the inner workings of the program. At the top right, I'm showing you a simulated transit light curve. And this actually came from a real exercise the team went through recently with real simulated TESS data. It's a bit of an oxymoron, real simulated, right? But simulated data where we went through this exercise to recognize TESS objects of interest, planet candidates, out of like a sea of a ginormous amount of data. So I want you to think of this funnel diagram of what's happening internal in the TESS community is thousands of transit light signals out of the hundreds of thousands of 2-minute cadence stars that we're monitoring. And we sort of go through different, now traditional for exoplanets, studies to sort of whittle them down to the main objects that have measured masses, that are small planets with measured masses. And I wanted to draw your attention, if you'd like some of these details, there's a poster session on Friday, and there's a few different posters there that will walk you through a lot of these things in a lot of detail. I just want to point out Dave Latham, who's sitting in the front row right over there. We have these objects of interest that MIT is leading this effort with human vetters and computer vetting. But once we see a transit light curve, this little drop in brightness, it could be many things. And thanks to Kepler and other ground-based surveys, astronomers literally have this down to a formula right now. And there are a lot of messy details I'm not going to go into, but you see this really nice chart that's showing you just this kind of two-tiered follow-up. But I just wanted you to know that TESS, it's not just finding these planets, but it's the follow-up program that will get us to the planets that literally hundreds of people from around the world are involved with. Ultimately, our data products are delivered to mass. Now, what I wanted to show you is this yield plot. This comes from a paper. I've listed the reference below. And this is showing you here on the y-axis. It's a logarithmic scale, so 10 at the bottom, then 100, 1,000, 10,000, 100,000. And you can see that there's different categories of planets in these bar charts showing you how many anticipated planets there are. It's just from a simulation of TESS and its noise budget and what would happen. So you see 70 or so Earths, hundreds of super Earths. And this is just sort of for your perusal. We'll see what actually happens when we get the mission going. There's one thing I wanted to share with you because there's so many exoplanet talks now and missions and projects. I divide it in a somewhat oversimplified fashion into kind of 4 categories. One is detection, one's characterization, and each of those for small M-dwarf stars and also for sun-like stars. So TESS is in the category of discovery mission. It's discovering planets. It's not characterizing them. It's literally just finding them so we can characterize them with follow-up measurements. And the second thing is TESS will really, let's say, shine with small stars because of its capabilities. It's not really aimed, although it will find interesting objects around sun-like stars, it does way better for small stars. So that's a point to help you navigate in the sea of exoplanet missions and projects. Now, following on to what George said, it's not so much the numbers of planets we care about, but the fact that they're orbiting very bright nearby stars. And I'm now going to show you an animation made by Zach Berta Thompson, where we're at the center and we're zooming out. Yellow is the predicted TESS stars with planets. Blue is Kepler, black is other. And you can see right now that within 10 or 30 parsecs, tens of light years, there's, wow, so many anticipated planets around nearby stars. And the pioneering Kepler mission, for its own reasons, focused on a field that was quite distant. But the value of these nearby stars is really the whole legacy of the TESS mission. And showing you a couple of other plots from Zach, it's now kind of deconstructing that animation to show you planet size. So it shows you 1 Earth size up to 5 Earth radii. And this is distance in light years now, so 30 light years. It's incredible, really, how vast space is, because even here, just a few light years, we don't have a whole lot going on in terms of transiting planets. And the Kepler stars here, you can see that they're quite far. Now, the size of the circle intends to show you how easy it is to spot the signal. And so it typically means they're small stars if there's a big signal there. And in terms of what TESS is predicted to find is to just fill in this chart for us with these very nearby host stars. Just let you enjoy that for a minute. And so in the notes when Zach prepared the slide, the one point to convey is that the difference between a planet at, let's say, 500 parsecs and one, let's say, at 50 parsecs, when we're thinking of now following up these planets to study their atmospheres, that would be the difference between requiring a 65-meter diameter telescope, which is way bigger than they're talking about even in the LUVOIR sessions, compared to the James Webb 6.5-meter telescope. So one of the whole goals of TESS, a subset of the community, let's say, is literally just dying to find all these planets and confirm them as planets, and then follow them up to look at their atmospheres with the James Webb Space Telescope. So now I'm going to turn for a couple minutes to talk about the so-called atmosphere opportunity. And this plot comes to us from Dana Louie, a graduate student at the University of Maryland. What she is showing you on this plot is planet size now on the bottom, 0.51, 1.5 Earth size. And this is what we just call signal to noise. For your purposes, kind of anything above 10 is good news. The higher it is on this plot, the better. It just means the better signal we get. And she's done a detailed simulation for this Webb telescope instrument called NIRISS. And these observations are about 10 hours. There's a lot of details in here, but this is just kind of bigger picture. And what she's showing you on the plot here, TRAPPIST, I think you all know those. So here's showing you with the James Webb, people are going to want to observe TRAPPIST. And she went ahead and simulated what the anticipated TESS bounty will be, assuming we have enough, well, these are the targets. It's not saying this is the actual program of follow-up. The community has to propose and succeed in proposing TESS. So it's literally just flooding our opportunity for studying exoplanet atmospheres by the transit transmission technique. And this paper, it's almost finished being reviewed. You'll be able to read about it. There's a lot of details on here about which are better, which have which type of planets, but for your purposes, it's just going to actually mean that there's a whole new era of exoplanet opportunity because the transiting planets are around stars that are bright enough for follow-up study. Okay, so now I'm going to spend a minute or so on this my final slide here, and this isn't any news for today. This is what you kind of can let mull over and digest and think about as the few years go by. Because in my mind, this is what I see as the true major impact that TESS will have. And I start out by rewinding back to the so-called olden days in exoplanets, where we studied individual objects. So HD 209458b, some of you may remember that one, big time. That was lots of papers only on that one planet. And then Kepler launched in 2009 and opened up this flood of big data for exoplanets. And there are tons of papers, thousands of planets and whole census papers and categories. And in this case, it was a wonderful, amazing change for astronomy. In that case, it's limited really to planet sizes and orbits. Nothing wrong there. But the point for you to walk away with is that TESS's bright planet host stars enables a combination of those two. We can do very detailed object studies, but on an ensemble of objects. And so I think we'll see this whole new opening for exoplanet studies. I had a few examples here. I only pick one to go into in detail. But let's take these so-called sub-Neptune-sized planets. Planets of 2 to 3 times the size of Earth, which are extremely common in our galaxy. We have no such counterpart in our solar system. And there's a bunch of theories on how they form and what they might be. There are probably a whole bunch of different things. But TESS will enable us to find tons and tons of transiting sub-Neptune-sized planets for which we'll have radii and masses, so we'll know their average density and bulk composition, and we'll be able to study these in great detail around different star types and of different kinds, and hopefully we'll make headway on what those planets are. And that was just one example. There's lots of examples. This is all being driven by the community through this. We'll hear a bit about the GI program, but also just general astronomers, graduate students, established astronomers, all sorts of people wanting to drive this new era of exoplanets. Thank you.
Good afternoon. My name is Padi Boyd. I'm at NASA Goddard Space Flight Center and the director of the Guest Investigator Program for TESS. Guest Investigator programs are meant to maximize the science return from NASA missions, and this is a really exciting time for me to brief you on the Guest Investigator Program because we have spent the better part of the last year and a half or so working very closely with the team at MIT and also with NASA headquarters to design a Guest Investigator Program that would have a very broad science reach for TESS. And we have just gotten through the peer review of the first set of guest investigator proposals for TESS, so I can give you a bit of a preview for the exciting science that we are expecting to get from the guest investigator program in exoplanets and beyond. So as George and Sara have both shown you, TESS has a huge field of view. There are literally tens of millions of stars when you look at the entire survey that TESS is going to do that are amenable to time domain analysis, time series analysis, making light curves and making discoveries based on the time variability of these objects. And the TESS science team is very focused on picking the best targets for exoplanet detection from the 2-minute cadence data and also from the full-frame images. And they are also very focused on prioritizing those for the ground-based follow-up to measure masses. And the point of the guest investigator program is to enhance the team's science. So the guest investigator program solicited proposals from the broad scientific community. It was purposefully left very open, but as long as you weren't duplicating the science team's projects, you could propose for TESS guest investigator funds. And TESS is a unique mission. The camera has a unique bandpass. It's actually going to stare at an object without blinking for 27 days minimum, and as you saw, almost a year in the polls. And that can give us all kinds of exciting science at the 2-minute cadence, which are those little postage stamps you can put on top of pre-selected targets, or on the 30-minute timescales, because we've got those full-frame images coming down, basically opens it up to everything that TESS can see. So the TESS team made available 20,000 targets that could be given out to guest investigator programs, as well as funding that could be used for analyzing the data on the 2-minute targets or for analyzing the data on the full-frame images. And these are awarded through a competitive program, just like other missions of this size and the larger missions. We solicit proposals from teams, and then we pull together a group of science peers, and we have them read all the proposals, discuss them, rank order them, and make a recommendation towards headquarters, for what will be the guest investigator program. And we are right now in the end stages of that. So very soon now, we will be communicating to the teams that propose to let them know if they were successful and what they can do next. So I mentioned that TESS has 2 different kinds of data products, and we are looking forward to science from the 2-minute postage stamps that can be put on top of individual sources. This is exactly the way that Kepler operated. And in that case, you have to be very careful to choose your target, and you have to justify that you actually need 2-minute cadence, 2-minute time sampling to get your science. Because again, we have those full-frame images, and they're being written every 30 minutes. So there's a tremendous amount of science that you can do just from the full-frame images. The advantage that TESS has over Kepler, of course, is that those full-frame images are being stored on the spacecraft and sent down so that basically everything in the TESS field of view can be investigated in some way or another. So our call for proposals closed in early October, and this is an overview that shows you the types of proposals that we received. We received well over 140 proposals, which was about 2 or 3 times more than we were expecting. So the community was really enthusiastic about this opportunity, and they responded in full force. You can see there that we got 53 exoplanet proposals. So those were proposals designed to do, again, exoplanet science, different than what the team is going to do, that would enhance the TESS exoplanet yield. But also, you see a huge fraction there of proposals looking at stellar astrophysics. Because we're looking at time variability of the objects, you can study flares, rotation, pulsation. We know that scientists are going to be studying the stars themselves to learn as much as they can about the stars. And in fact, that was our biggest category. We also had proposals that came in to do extragalactic science. So what can you learn about galaxies by studying their time variability on long timescales with no gaps? You can actually do quite a lot. We saw that Kepler had some really cool extragalactic programs, and there were some good ideas for TESS as well. And there were even some proposals that came in to do solar system science. So solar system objects will come into the field of view. They will vary with time, and those variabilities can tell you something about the solar system objects. So it was a great sweep of science. It was very exciting. And the program that was proposed represented between 4.5 and 5 times the resources that we could actually give out in the program. So it was extremely competitive. So I'd like to give you a bit of a preview now for some of the science that we expect to see from the guest investigator program. And I'm going to be using Kepler and K2 missions to sort of whet your appetite. So this is a ground-based image of the Pleiades. It's an open cluster that you can see in the winter sky near Orion. So if you're familiar with the constellations, you can go out, look for the Tiny Dipper. That's the Pleiades, 125 million year old, very young star cluster. Those 7 sisters that we're all used to seeing are all very large stars, bigger than the sun, more massive. They're what we call B stars, bright. So Kepler had a program that was designed to take photometry of these bright stars, even though they actually bleed out of the aperture on Kepler. They were visible in K2, and if you used big apertures, even though lots of your pixels are bleeding out, there's the pixels in the halo that can give you great information about the variability of these stars. It's called halo photometry, and there are some folks here at the meeting and some posters on halo photometry for Kepler and K2. What you can see there is that this is not a beautiful image. It doesn't need to be. What we're actually after are the time variations. And on the right, you see all the stars. You can map the colors to the light curves. We're able to get extremely high precision light curves of these stars. They're all about the same mass. They were all born into the same family at about the same time. But you can see a variety of activity and behavior between those 7 sisters. And if you grew up with some sisters, you know that that's not uncommon for people in the same family to act very differently if you watch. And in particular, the Maya, M-A-I-A there, is a Maya variable. It doesn't actually show Maya variability type behavior. It has a long 10-day period. None of these periods could be detected like that from the ground. And TESS is going to have so many bright stars in its field of view all the time. We're going to be seeing a lot of advancement in our understanding of the bright nearby stars. Another example that's very exciting is something called galactic archaeology. And this is something that Kepler really broke open and that K2 continued to add sources for. So the idea behind galactic archaeology is to use red giant stars, stars that are not interesting for finding transiting planets and pretty much impossible to do so. But they oscillate, and they oscillate in such a way that you can combine that with ground-based measurements to get really fundamental information about their ages, their evolution, their chemical composition. And so scientists are using all of the giants in the Kepler and K2 fields to put together a picture of our galaxy and the stars in it, how they evolved, how they formed, how they might be looking in the future. We don't really know that about our own galaxy. We're going to find that out about our galaxy, and we can apply that to galaxies beyond, something that K2 and Kepler were not meant to do, but can make a great impact on. Another example that was really exciting from Kepler and K2 was that when a supernova went off, if they were actually already observing the galaxy, you could get the supernova light curve on the rise. So for example, we saw the first shock breakout from a core collapse supernova, watching that blast wave interact with the star surrounding it. We know that TESS is going to see some transients that are going to be triggered from other instruments, and we'll have those pre-discovery light curves. We can watch those transients happening. We just don't know which ones they are yet. So very exciting for transient science as well. And maybe the most exciting transient that we've heard about in the last year, the electromagnetic counterpart to a gravitational wave source. This is a simulation of what TESS might see. We know from the first one that we saw that it does stay bright in the bandpass that TESS is for quite a while. So we're hoping that with TESS, just serendipitously, we may be able to interrogate some gravitational wave electromagnetic counterparts, just because of the way the mission is designed. And that's really exciting for not just the exoplanets community or the stars community, but even the gravitational wave community. So my takeaways are that we were very excited to see how the broader scientific community really responded to this opportunity, the guest investigator call. The ideas that they've proposed are very exciting. We're right now in the final stages of announcing what the guest investigator science will be like. I would say look for that in about a month or so. And we will then be working with the team at MIT to get those targets uploaded onto the spacecraft. And so it really looks like the guest investigator program is going to have a great impact on TESS science, and we're really excited to see what happens in the next couple of years. Thank you.
Okay, great. Thank you for coming. My name is Elisa Quintana. I work at NASA Goddard Space Flight Center as a TESS support scientist. And I'm here to talk about why the entire exoplanet community is really excited about TESS, given where we are now and where we know we're going. And so I think many people here probably have worked on communicating a lot of the Kepler discoveries over the past few years. And so I just wanted to give a comparison of what Kepler's goals are compared to TESS. And so Kepler's primary goal was a statistical mission to determine what fraction of stars in our galaxy harbor Earth-sized planets. And if you see this box in the upper left, that shows the Kepler's field of view on the sky that it observed for over 4 years. And what we found are that planets are everywhere. So these are the locations of many of the planets that were just found in the first few years of data. So Kepler taught us that planets are common. And given that planets are common, we can take the next step. And so TESS' primary goal is to search for small planets around nearby bright stars that are amenable to follow-up. And so you can see on the left, again, I've placed TESS's field of view over Kepler's. So you can see the relative size difference. And as George talked about, TESS is going to tile the sky with its 4 cameras to cover about over 85% of the sky. And so Kepler planets were of order thousands of light years away. And the field of view really only covered about a fraction, 25% of, or 0.25 of 1% of the sky. And so TESS is very different. TESS is going to observe most of the sky, and it's going to look for planets around stars that are within hundreds of light years from observers. And so that's really exciting. So here I'm showing all of the stars that are located within 80 light years of the sun. The stars are colored by spectral type, and they're sized by luminosity class. So it shows some dwarfs and giants. And so you can see M dwarfs, shown in orange and red, really dominate the stellar population for planets that are nearby. And so in fact, M dwarfs compose about 75% of all of the stars in our galaxy, so they're really abundant. Most of the M dwarfs are faint, so if you were to walk outside and look for them, you wouldn't be able to see them without a telescope, but they are our nearest neighbors. And so TESS is really going to find many planets around a lot of these small stars, and it's going to be really excited to see what they find. In fact, our nearest star is a red dwarf, Proxima, and we already know it has a planet. And so here's a comparison of M dwarfs with sun-like stars. On the left, here is a Earth-sized planet in the habitable zone of a sun-like star. And on the right, we've placed an Earth-sized planet in the habitable zone of an M dwarf. And so M dwarfs range anywhere from 10% of the size of the sun to 50%. So this is more towards the larger size of M dwarfs. And because these types of stars are really cool and dim and have low luminosity, their habitable zones are located much closer into the star. And so the planet on the right, because the star is smaller, is going to block a larger fraction of the light that we're observing. And this produces a much deeper transit. And so planets around M dwarfs are much easier to detect. Because these planets orbit much closer in, their orbital periods are shorter, and you get many more transits in a given time compared to Earth-Sun analog examples. And so I wanted to talk about why getting masses is so important. And some of the most valuable planets we have are those with sizes and masses. And so we know that Kepler just really provided planetary sizes, and we never really had a good population of planets with both measurements. And so here on the top, I'm showing an Earth-sized planet. And if we don't know the masses, they could be composed of anything within the spectrum. This is just an example of, it could be a pure ice ball, which it would have a be very light and low density, and be very have a low mass, or it could be something like more high iron heavy. And so without a mass, we don't really know what it's composed of. TESS's follow-up program is going to help break these degeneracies, and we'll measure the masses of at least 50 planets. And so I think this is going to really contribute to our understanding of differentiating between Earths and super-Earths and mini-Neptunes, and try to understand how they, what the differences are, and also shed light on how they form. And so Spitzer and Hubble are going to continue to follow up a lot of the planets that TESS finds. Right now, we have about a dozen planets, dozens of planets where we have measurements of atmosphere properties. And we've really been testing the limits of these, both of these spacecraft. And so James Webb promises larger and more sensitive equipment to really boost the atmospheric characterization of exoplanets. And as Sara showed earlier, TESS is going to provide a large number of great targets for James Webb. And so Webb will use its infrared instruments to really probe planetary atmospheres. Plans for early release science with James Webb have already been announced, and Transiting Exoplanets has one of the largest programs. So everybody's already really excited for what is to come with the synergies between TESS and James Webb. And here's another illustration of the exoplanets in the future, both NASA missions and non-NASA missions. This shows more missions and surveys than the slide that George showed earlier, because I just wanted to emphasize that this whole field of exoplanets and the future is really a worldwide endeavor. There are people all over the world that are involved in characterizing exoplanets and pushing the field even further, along with a large suite of ground-based, both big and small programs. And so scientists are already thinking about what we'll do with the next great observatories and what's next for characterization. So there's a lot of exciting studies to be followed up even beyond Webb. So here are my takeaways. TESS will catalog many planets around nearby stars, many of which will be small, cool M dwarfs. And TESS will find lots of planets smaller than Neptune, at least 50 of which will get masses. And with masses and radii, you can infer planetary compositions, and this is going to yield high-value planets for further both observational and theoretical studies. And finally, TESS planets are going to be the touchstone targets for atmospheric characterization, as Sara showed, for future missions and for decades. And finally, I just want to add that Frank Reddy and Claire Saravia put together a nice science writer's guide that you can download at nasa.gov/TESS. It's a nice document that covers everything from the mission and the observing strategy and the team and contacts. And so I highly recommend that you download this. Thank you.
Thank you all very much. I think that covered a lot of good ground, and now we'll take some questions. So if you have a question here, raise your hand, and Frank Reddy's going to bring a mic around. Wait for a mic. Let us know who you are and who you write for, and if you're addressing your question to a specific person. And then if you're on the webcast and if our chat system is working, please queue up your questions there. So we'll start down here.
Seth Borenstein, the Associated Press. I guess maybe for Sara, but others feel free to jump in. Given more recent studies that keep showing issues with exoplanets and habitable zones near red dwarfs, can you characterize more how many sun-like planets, planets around sun-like stars you expect to see with TESS? And is there any chance of prioritizing those given their issues with atmosphere disruption? with M-dwarfs, and how does that factor in here? Are you basically looking in, as the old joke goes, in where you have the light as opposed to where your keys may have fallen?
Yeah, we're mostly looking where our keys, where the light is. I would just say that the great thing about astronomy is it's an observational science. And I sometimes think of myself in both the theory and observation side, but the observation people always say, well, they don't care about theory. Whatever the theorists come up with, don't worry about that. We'll see what's out there. And so with TESS and James Webb, we can definitely study the small rocky worlds and see if they have atmospheres, see what's actually going on. With respect to sun-like stars, again, remember when I said I separate things out into characterization as opposed to discovery? Even if we can find small rocky worlds around sun-like stars, it will be nearly impossible to study their atmospheres with the transit technique, because it's like that skin of the onion against the backdrop of a giant star. So you won't get all the answers. It won't be comprehensive across all types of stars. However, I think we can, I don't want to, one thing we never want to overpromise, but if the planets are there, we can study them with the James Webb and help sort through things.
Alex Witzy with Nature. My question is for Dr. Ricker. Could you update us on the camera focus issue? We learned last summer that the performance was not quite as designed. What does that mean for your science objectives, and specifically the numbers of planets that you're looking to discover?
Sure, I'd be happy to do that. In fact, I've got a slide that might be helpful in that area. I know this is a topic that there's been quite a bit of confusion relating to, and I'd be very happy to help clear that up now. Okay. One of the things that I think is important to understand is that there's been a bit of confusion between what you mean when you talk about focus stability and when we talk about focus drift. So different words have been used to describe what the actual concern was that was raised in the discussions last summer. What we did see initially when we started working with the flight cameras about a year ago was that, that we saw shifts in the focus that were not predicted by the initial optical models. And subsequent testing that we did starting this summer and then into the fall indicated that there is a model for what we understand. This was a very reproducible crystallization effect for one of the materials that was actually used to manufacture the lenses themselves. It's a elastomer that acted as a shock mount. So what we've done subsequently now for more than 6 months is that, and 4 months of testing on the flight spare unit itself, is to observe this property in terms of the impact that it has on focus. And what we find is that the way the lenses actually behave is there's a 1 week focus settling time that's required, and then there's no, essentially no measurable change after that time has elapsed when we're operating at the actual temperature that the lenses will have in orbit. So it really is best to describe this as a focus shift and not a focus drift, because once that quiescent level is reached after the settling time, there's really no effect that we can actually see. In fact, when we measure this effect, we see that the shifts are in the submicron range, so they have no impact on the focus of the lens itself. Now, the other thing is that, to answer your question about how that impacts the science yield, it has no impact that we are aware of on the level 1 requirement that the mission had, which is to establish 50 measured masses for planets with less than 4 Earth radius in size. And then the other thing I think is, in general, even for the astrophysics that are not related to exoplanets, it's important to keep emphasizing that this is a photometry mission and not an imaging mission. And what this means is that it's important to not have a sharp focus across the entire field of view. I mean, this was never part of the design, but it is important that the focus be stable, and that's what we've been able to establish. Looking forward, if there are long-term slow changes in the in the focus, similar to what Kepler observed, there's no problem in terms of the yield for the mission as a whole.
Is that focus settling just a one-off?
It's a one-off, exactly.
Govert Schilling, freelance from the Netherlands. I was wondering about the operational lifetime of TESS because at some sites it says it's 2 years. You mentioned maybe a couple of decades. If probably a matter of funding. If that happens, is 2 years a minimum? And if it can be extended, will you shift between northern and southern hemisphere all the time? And does it give you the opportunity to find long period planets too? That's one question. I mean, the other question was, is there a prediction, an expectation for the number of new planetary candidates that we may expect, for instance, in the first year of operation?
Okay, well, in terms of the actual mission lifetime, I think one of the things you said is correct. TESS is not going to be limited by any expendable or other aspects. It's going to be basically limited by how long NASA has the patience to fund the mission. The primary mission was selected for 2 years because that's pretty standard for an Explorer mission. We will undergo a senior review by NASA next year in 2019, and at that point, if we're selected, the mission will then go for an additional 3 years. And as I said in one of the slides related to the orbit, we've done analyses that show the stability of the orbit extends out for many decades. So I think that we could very well expect TESS to last in orbit as an operational mission for times comparable to Chandra, for example, which has gone now for 19 years, and the type of results that we will have will improve accordingly. One of the things that you get out of an extended mission for TESS is that if you do repeated observations of exoplanets as the mission progresses, you refine the orbits much better. Therefore, when missions like Chandra, or sorry, missions like Webb or even Chandra for some of the non-exoplanet targets, if there's a periodic phenomenon that you're looking for, you'll refine the ephemeris more and more precisely, and that means, for example, for exoplanets, that we will be able to predict the ingress and egress times for the transits much more accurately. And this will certainly even conceivably extend to the sorts of things that you'd be able to do with the next generation observatories that are actually being planned. There's no other mission other than TESS that will be able to carry out these types of observations until the late 2020s, when the Europeans will launch this mission, this very ambitious mission called Plato, which will offer a lot of additional power for observing exoplanets, and I think that will be sort of the next chapter. And you had a question related to the number of targets and the types of observations that we can make. TESS was deliberately designed so that it could execute a number of different observing scenarios in future missions. We could stare at one particular stripe, 24 degrees by 96 degrees wide. If we rolled the spacecraft over 90 degrees from what was shown in the animation, we can look at we can revisit the ecliptic, which is where K2 has made a lot of its observations. We could actually focus even more directly on other parts of the sky, including the north and south celestial, the north and south ecliptic poles. So there's a lot of observing scenarios, and in fact, there's a paper that's on AstroPH that describes 6 or 7 such scenarios that we've already entertained. The expected number of discoveries in the first 2 years were described in that slide that Sara showed, and there's a follow-up paper to that's also an AstroPH that I could give you the reference for later on.
I think it was about 20,000, right?
Yeah, there's at least there's of order of 15,000 Jupiters, and if you calculate the total amount from the ones that are in the smaller category, that number is around 1,500, and it would some of the simulations that we've shown shows that number would grow by about a factor of 2 from one extended
It will
mission.
take a while to propagate through the follow-up program, so
Right.
we don't have exact numbers for you at this
Yeah.
point.
Yeah, I'm just speaking of candidate objects that we identify that then have to be validated in the follow-up program.
Hi, Lisa Grossman, Science News. I was wondering how long will it be between when the telescope launches and when you actually start taking data, and what will the time gap be between when you start taking data and when James Webb starts taking data? So how long will you have to identify planets for James Webb follow-up, and how many do you think you'll get before you're observing in sync?
Okay, yeah, I can answer that. The launch is planned for late March, and then there's a 2-month commissioning phase, and then the survey should start in June. So that provides approximately a year before Webb actually is launched. And I understand that the operations with Webb would start in late 2019. So there's about an 18-month lead over Webb. That would, during that period of time, we would have completed the full survey of the southern hemisphere and about half of the northern hemisphere. The item that's going to be most demanding, of course, is the follow-up program to make sure that planet candidates, which are identified based on their radius, can then have masses that are established from precision radial velocity follow-ups. This was the diagram that Sara showed.
I mean, everyone on the team wants this, so I don't think we have to worry that we won't be moving through those objects to have stuff ready to propose to observe.
Right.
We'll take one more down here in the front. And do we have any online, Larry? No, we're running out of time anyway, but I see there's one more in the back. Okay.
Hanukkah Whitering with Space.com. My question is for George. So you said that TESS is looking for good candidates for follow-up observations, but I'm wondering, does that mean that there is such thing as a bad candidate, like a newly discovered exoplanet that you don't want to look at for some reason, or is it all just about allocating the resources with James Webb?
Well, I'm not really sure quite what to say about that. Is there a bad planet? I think the only way in which there's a less desirable planet is if it's associated with a fainter host star, or it's something that's detected at a low signal and noise level. The time on Webb is going to be so precious that you're going to be really you want to be really sure that what you've found is an interesting object. So the time on Webb is going to be so heavily oversubscribed that we're only going to try to bring the very best candidates to Webb for consideration.
But I would like to add something, and after this is over, you should come over here and talk to Dave Latham, who just gave a very violent yes to there are bad planets. But there's a lot of different
That's because he's a stellar astronomer.
There's a lot of different things happening. There's this core team represented here, and we have our goal, our obligation from the proposal to deliver the best 50 planets with masses, and for us wanting to find the so-called habitable worlds. But there's this kind of overlapping Venn diagram that has many different options. So for others, there may be other categories that are extremely valuable. And the legacy of TESS is this catalog that will live on for the lifetime of James Webb and beyond, so it will be mined. We're just telling you like the immediate goals of this group, but the TESS legacy is the catalog for posterity.
And then Dan.
Hi, Dan Cleary from Science Magazine. You talked about the importance of the follow-up program. Can you tell us a bit more about that? Who's going to be following up? What instruments they're going to be using?
Yes, again, I'll refer you to Dave Latham for after the meeting. He's right here, and he's at CFA. They're organizing the follow-up program. But essentially, it's divided into 2 categories. One is TESS-funded follow-up. So there's things like LCO, which actually is doing what we call reconnaissance spectroscopy to get a better handle on the stars and what's going on there. And you can also look at our website, tess.mit.edu, which will walk you through the different steps. And there's actually different leads for different subgroups. You could even, if you wanted, contact them. A lot of them are here at the meeting at large. And there's sort of ways to figure out whether it's a false positive or an actual planet. And there's ways to get coarse rate of velocity and follow up by fine rate of velocity to know what's going on. But I would say it's fair to say it's still evolving. And there are a lot of people involved, led by Dave, and there's key leaders for each subgroup. And so how that will actually pan out is still actually evolving. But you should know, though, that there are many groups that do this already for K2, for example. So this sort of already exists. It's just a matter of organizing it in a coherent fashion. And the second part, as opposed to the funded follow-up, is just the different contributors volunteering their telescope time from around the world. And this will be also aided by a website called Exoplanet, led out of Nexi. These are a lot of